Cuttlefish. Aye, let us not, dear friends, forget our dear friend, the cuttlefish. Flipping glorious little sausages. Pen them up together, they'll devour each other without a second thought. Human nature, in it. Or fish nature. So yes, we could hole up here, well provisioned and well armed. Half of us would be dead within the month, which seems quite grim to me, any way you slice it. Or, as my learned colleague suggests, we can release Calypso, and we can pray that she will be merciful. I rather doubt it. Can we pretend she's anything other than a woman scorned, like which fury hell hath no? We cannot. Res ipsa loquitur tabulin naufragio, we are left with but one option. I agree with, and I cannot believe the words are coming out of my mouth, Captain Swan. We must fight.
All right, folks, last time we were discussing the biosynthesis of cholesterol, where we first described the preparation of isopentenyl pyrophosphate and dimethylallyl pyrophosphate, both 5-carbon isoprenes, from acetyl-CoA, first via a Claisen reaction to generate this beta-ketothioester, and then via an aldol reaction where an enolate of acetyl-CoA attacks the ketone, and we get this intermediate where after thioester hydrolysis we get hydroxymethylgluteryl-CoA. We discussed how this aldol step was key to establishing the branching methyl group that is present in IPP and DMAPP. We also discussed how reduction of HMG-CoA is the step that's inhibited by statins. We talked about how this process occurs based on hydride delivery to the thioester to get an aldehyde, and then again hydride delivery to the aldehyde to get this alcohol mevalonate. And they call this pathway the mevalonate pathway because of this key intermediate. The next few steps are to establish the pyrophosphate group that's going to be important to us later on in the chemistry of these IPP and DMAPP monomers. So first we use ATP and mevalonate kinase to phosphorylate this primary alcohol. Then we do it again with phosphomevalonate kinase, consuming another ATP. That gives us the pyrophosphate. And then in order to get from mevalonate pyrophosphate to our 5-carbon IPP or DMAPP, it looks like we need to lose this OH group and lose this CO2 group. Normally, when we lose CO2 groups, that's decarboxylation. We've done decarboxylation before when we had a beta ketone, a beta carbonyl group. We can't have that here because, of course, the beta hydroxy group is actually on a tertiary carbon, so no oxidation is possible. However, if you can imagine the electrons on the oxygen kicking down to make CO2, you could have the electrons in this bond that would go onto the alpha carbon then collapse down and kick off some leaving group if we had a good leaving group. So the next step of the reaction is to use another equivalent of ATP to phosphorylate the OH group in pink. Then the leaving group leaves. You've got a positive charge on the beta carbon, and then the electrons on the oxygen can kick down to release CO2. Electrons in the alpha carbon to carbonyl bond sweep over and become a new pi bond between alpha and beta carbons. That gives us isopentenyl pyrophosphate. Now, that is one of our important precursors. However, we're going to need another, and the mechanism to convert from one to the other is actually quite simple. It's just tautomerization, really. So we remove the proton that is adjacent to the pi bond, that gets us to this resonance stabilized anion. And then we can protonate that anion on the methyl group, and that gives us the dimethyl allyl pyrophosphate. Now, why would we want to move the double bond over like that? Well, remember that pyrophosphate can actually be a good leaving group. And the chemistry that we're going to do is going to rely on the ability of this pyrophosphate group to leave from that primary carbon to which it's currently connected. However, that primary carbon is adjacent to a pi bond, and so if pyrophosphate left, you get a resonance stabilized intermediate. So we're going to see that in subsequent steps, as we build up longer carbon chains from these precursors, that DMAP is going to be our electrophile, because it's the one that pyrophosphate can leave from to give you a resonance stabilized carbocation intermediate. Oops, like that. And then we will see that IPP will be our nucleophile, because the pi electrons in IPP, the HOMO of IPP will attack the LUMO of this carbocation. And this is conventional, typical addition to alkenes chemistry. We're going to form the new bond let me just label things real quickly. We're going to form the new sigma bond between the less substituted carbon of the IPP alkene and the carbocation, so that the more substituted tertiary carbon can have the positive charge. So this would be the new bond that we made. And then this would be our intermediate, whereupon we can do sort of E1 style elimination of this proton that's adjacent to the carbocation and get our product. Condensing two of these isoprene units together gives you geranyl pyrophosphate. And notice that we are, again, in a situation where we have the pyrophosphate leaving group adjacent on a primary carbon that is adjacent to the pi bond, such that if this pyrophosphate group left, we could have a positive charge that's on that primary carbon that's resonance stabilized. Okay, so important features of this reaction. SN1 sort of style, leaving group leaves, carbocationic intermediate, only this time the nucleophile is a pi bond. We're going to make the new sigma bond between the less substituted carbon and the carbocation, such that the positive charge can be on the more substituted carbon, and then we're going to eliminate to give the more substituted alkene product. So the regioselectivity is governed by carbocation stability and alkene stability, all principles that you understand from 351. The next reaction is going to see us bringing in another equivalent of isopentenyl pyrophosphate, which will again be our nucleophile. The mechanism here is going to be the same as in step 9 on the previous page. And when we're done, we will have elongated our molecule by 5 carbons. So now we have farnesyl pyrophosphate with 15 carbons. And I've labeled each of we call them isoprene units, these 5 carbon units that come from either IPP or DMAP. I've labeled each of them in different colors so you can see 5, 10, 15 carbons in farnesyl pyrophosphate. Okay, so the next step is one that you don't have to worry about the mechanism. And a couple of interesting things so far before we get there. Notice that terpenes, or these molecules with these types of structures, with these isoprene units, are called terpenes. And you'll notice that terpenes have some directionality. You identify the carbon that has 2 methyl groups on it, and that is sort of the head. Well, now let's say it this way. You identify the carbon that has the pyrophosphate group on it, that is the head. And then the carbon that has the 2 methyl groups on it, that is a tail. And you can see that as we add new isoprene units, we do so head to tail. In other words, we connect the head of one of our products with we connect the head of GPP to the tail of IPP. And we've got this same head to tail directionality, okay? However, and so if we look at the next step, we have 2 molecules of farnesyl pyrophosphate oriented from head to tail, each of them 15 carbons. We're actually going to react 2 of those together. We're going to need an equivalent of NADPH, which is just like NADH, only with an extra phosphate group. The key change here is that these 2 terpenes will be connected head to head. And that is unusual for terpene chemistry, where you normally connected things from head to tail. And the head-to-head connection requires a reducing agent. The step is kind of interesting. It's kind of complicated, though, and it's beyond the scope of the class. So here's squalene, now 30 carbons. 1, 2, 3, 4, 5, 6 5-carbon isoprene units. Molecules that have two isoprene units are called monoterpenes. 4 isoprene units would be a diterpene, and 6 isoprene units would be a triterpene. Of course, farnesyl pyrophosphate with just 3 isoprene units would be called a sesquiterpene, or a 1.5 terpene. So in the next step, squalene gets, the terminal pi bond of squalene gets oxidized by squalene monooxygenase using oxygen and FAD to give you the squalene epoxide. And again, you don't need to worry about the mechanism of this step. It's known and it's not that hard, but it'll be beyond the scope of the class. Now, if you think about, and I suppose it would be good to give you a sense for the kind of structure we want to get. Cholesterol and other molecules like it have this characteristic structure that has 6 plus 4 is 10, plus 4 is 14, plus 3 is 17, 18, 19, 20, 21, 22, 23, 24, 25 carbons. So we already have more than enough carbons to make the basic skeleton of a steroid. So I'm going to rearrange this molecule in a way that sort of starts to show you the connections that are going to be made. And the enzyme that does this is called squalene cyclase, and it will bias this process towards one particular enantiomer. But all of the arrows I'm about to show you in this cascade of steps that brings this molecule together, all of these arrows you can rationalize based on things you learned in 351. For example, some acid, perhaps in the enzyme, will protonate the epoxide, and that would generate a positively charged oxonium ion. Now, think way back to 351. Where do protonated epoxides get attacked? Pause if you need to and go look it up or remember. Okay, that's enough. You may have looked up that or remembered that protonated epoxides get attacked at the more substituted carbon. The reason for that is the protonated epoxide starts to leave from one of the two carbons that the oxygen's bonded from. The protonated oxygen starts to leave from one of the two carbons that it's bonded to, and it will leave from the more substituted carbon so that the buildup of partial positive charge on that more substituted carbon is better tolerated. All right. So of the two carbons in the epoxide, the more substituted one is going to be more electrophilic. So now with the partial positive charge on the more substituted carbon here, notice how that carbon is placed very close to the pi bond in the orange isoprene unit. And of course you know that pi bonds can be nucleophiles, and so it would be reasonable to imagine this pi bond reaching over and attacking the more substituted carbon and to make a new sigma bond there, and then breaking the carbon-oxygen bond from the epoxide, and electrons going on to that oxygen. And if we wanted to, we could actually condense all of this and show those electrons going to pick up the proton. Now, if we were to ask, of the two carbons, more substituted and less substituted, involved in the alkene in the orange isoprene unit, which one is going to get the bond with the purple tertiary carbon here? It's going to be the more substituted one or the less substituted one. And if you said more substituted one, remember that the pi electrons are pulling away from one of those two carbons and forming a new sigma bond. If we form the new sigma bond here between this less substituted carbon and this purple carbon, we'll make a six-membered ring. In contrast, if we form the bond here, that would be a five-membered ring. So we're going to make the bond here to make a six-membered ring, and that's going to have the added benefit of building up partial positive charge on that more substituted carbon. All right. Now, we can see, and you know what? I'm thinking maybe it'll be nicer for us to have this discussion if we at least number the carbons in the isoprene units. So let's take a minute to do that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And pink 1, 2, 3, 4, 5. All right. So there's a buildup of partial positive charge on carbon, orange carbon 2, where it's more stabilized because of hyperconjugation. But that orange carbon 2 is actually fairly close to pink carbon 4. And if we have the pi electrons from this bond between pink 2 and pink 4 pull away from pink 2 and go to forming a new sigma bond between pink 4 and orange 2, that would cause a buildup of partial positive charge on pink 2, where it would be more stable because of what you learned about carbocation stability. More substituted carbocations are more stable due to hyperconjugation. All right. Notice in turn, we'll put the positive, partial positive there, that pink carbon 2 is close to green carbon 2. And if we connected green carbon 2 and pink carbon 2, we would make a 6-membered ring. Now, if we make the new bond between pink 2 and green 2, that's going to cause a buildup of partial positive charge on green 4, which is the less substituted of the carbons. So you're going to have a trade-off. You can either make the more stable carbocation and the less stable 5-membered ring by connecting pink 2 and green 4, or you can make the more stable 6-membered ring by connecting pink 2 and green 2, but then you've got to have a buildup of partial positive charge on the less substituted carbon. And it just so happens that in this case, ring strain arguments dominate, and we're going to have a buildup of partial positive charge on carbon 4. That's okay, because almost immediately you've got the pi bond between yellow 2 and yellow 4 that are very, very close, and perhaps before even the full carbocation forms on green carbon 4, we have the pi electrons in the bond between yellow 2 and yellow 4 attack green carbon 4. We'll make a new bond between yellow 4 and green 4 here to make a 5-membered ring so that we can have the more stable carbocation on tertiary carbon 2. So you may be confused as to why we get the 6-membered ring here and the less stable carbocation versus the 5-membered ring here and the more stable carbocation. I don't have a good answer for that. Its typical hand-wavy cop-out explanation is, well, the enzyme makes it do that. However, there have been some people that have done some fairly sophisticated quantum level calculations suggesting that this pathway is the lowest energy one. And so, though I don't know why, you can perhaps accept the fact that it's okay to make a 6-membered ring here and a 5-membered ring here, and that's the lowest energy pathway versus a 5-membered ring here and a 6-membered ring there. In any case, once we have done that cascade of cyclization reactions, protonate the epoxide, attack and open the epoxide, attack the nascent carbocation there, attack the nascent carbocation there, attack the nascent carbocation there, we have taken a 30-carbon precursor with no rings and stitch together this complicated structure with 4 fused rings. A 6-membered ring here, a 6-membered ring here, 1, 2, 3, 1, 2, 3, 4, 5, 6. Another 6-membered ring here, a 5-membered ring, and then this alkyl tail. Cyclization gives you this protosterol cation, and what happens next is a series of carbocation rearrangements that get us to the final desired product. So you learned about carbocation rearrangements in 351. You learned how a carbocation on an sp2 hybridized trigonal planar carbon, a carbocation is associated with an empty p orbital. This adjacent carbon-hydrogen bond, sigma bond, can engage in sigma to p hyperconjugation, and in fact can actually take the hydrogen can actually take its electrons and lean over completely to make a new carbon-hydrogen bond up here with this tertiary carbon and leave behind a partial and leave behind a carbocation on the other carbon. And is it going to be helpful again to number atoms? 1, 2, 3, 4, 5, just so I don't have to keep saying this carbon here and that carbon there. Here a carbon, there a carbon, everywhere a carbon, carbon. Old MacDonald had a carbon. E-I-E-I-O. Sorry. You know what, though? This is the last lecture. You were almost done. And you will have survived OChem. I guess you will have survived OChem after you take the final. So, the carbon-hydrogen bond on yellow 4 can lean over, take its electrons, and attack the carbocation on carbon 2. As that happens, as that is happening, you've got a buildup of partial positive charge on yellow carbon 4. And at the same time, a carbon-hydrogen bond on yellow carbon 4 at the same time, a carbon-hydrogen bond on yellow carbon 4 can lean over and can do a 1,2 hydride shift. That would lead to a buildup of partial positive charge on green 4. The adjacent methyl group can do a 1,2 methyl shift. And that would leave a buildup of partial positive charge on green carbon 2. The adjacent pink methyl group can do a 1,2 methyl shift, which would, in the end, leave now a full positive charge on, after the process is done, we would have a full positive charge on pink carbon 2. I feel like that was confusing, so let's look at it from this above perspective. I'm just numbering the carbons again. All right, so the proton on yellow 4 is going to lean over with its electrons to attack the positive charge on yellow carbon 2. At the same time, the proton on carbon 4 is going to lean over and take the place is going to lean over and attack the nascent carbocation, or rather the positive charge on carbon-4 that will be forming as this proton does the rearrangement. So, and then as the proton on green 4 is shifting over to yellow 4, the methyl group on green 1 will shift over to green 4. And as the methyl group on the methyl group on green 2 is shifting over to green 4, the methyl group on green 3 will shift over to, the methyl group on pink 2 will shift over to green 2. Let me say that again because I feel like I keep butchering it. The proton on yellow 4 does a 1,2 hydride shift to attack the carbocation on yellow 2. At the same time as that is happening, the proton on green 4 does a 1,2 hydride shift onto yellow 4. At the same time, the methyl group on green 2 does a 1,2 methyl shift to green 4. And at the same time as that's happening, the methyl group on pink 2 does a 1,2 methyl shift to green 2. This may be stepwise. Some of the data or some of the calculations suggest there's sort of a really broad transition state without any lower energy intermediates. But after this series of 1,2 carbocation rearrangements, we will have, as I said before, a buildup of partial positive charge on pink 2, and then a base can actually do in the same step an elimination reaction where we remove the proton on pink 4 and the electrons kick down to form a new pi bond between pink 2 and pink 4. Or if we were going to show that over here, we would simply show those arrows. So after those 1,2 carbocation rearrangements, we're left with the following product, which is called linosterol. And linosterol is a precursor to cholesterol and all of the steroid hormones, and it's synthesized. This very complicated structure is synthesized from very simple precursors. The bonds that we made appear in red, but I'm also going to highlight the rearranged groups. And so this process is happening in you right now and is happening faster than we can even talk about it. So that's unfortunately all the time we're going to have for metabolism. And I want to spend the remaining few minutes we have together talking about polymers. Because of all the things we could talk about that you'll encounter in your daily life, aside from the metabolism that's going on inside you, polymers are perhaps the most important. So you may have heard of a polymer called polyethylene, or PE. And it actually sometimes comes in a couple of varieties, low-density polyethylene and high-density polyethylene. Polyethylene is prepared via a process called radical polymerization, wherein you have some radical initiator. We're going to pretend it's like a peroxy radical. And then you have ethylene, and you do a radical propagation step wherein you make a new bond between your radical initiator and ethylene, and then you have a new radical at the end of the ethylene molecule, and you can bring in, I guess we'll highlight that one in purple, you can bring in at that stage another ethylene molecule. We'll highlight it in orange. And we can do a radical propagation reaction where we form a new sigma bond between the primary carbon on purple, where we form a new sigma bond, and then the radical goes out on the distal carbon, and then we've got two ethylene units mixed together. Purple, orange here, sorry guys, purple here, and so we might continue until we have an arbitrarily long chain where each of these two carbon units that I'm highlighting has come from a different molecule of ethylene. Running out of colors to use. And we'll just put an N in the middle. Sometimes people do that with polymers. N is an integer and can be huge. And we can control how long the polymerization goes by how much initiator we put in relative to ethylene starting material. At the end, we can terminate the chains, perhaps by having two different elongating chains find each other. And that would complete the process. There are a couple of other, and I'll show you the bond that we just made in pink. There's a couple other termination processes, but we won't worry about them in this class. These are the propagation steps. So in the end, you have this very long hydrocarbon chain, and you might expect it to have properties similar to wax. Now, it turns out that depending on what you do, depending on how you run the process, some radical processes can actually result in not only linear chains, but also branched chains. The long linear chain of polyethylene packs efficiently against itself, so I'm just going to pretend that we've made this really, really long polymer. By the way, I guess I should say that the polymer ends up being so huge that there, in terms of the number of atoms, there's way more polyethylene part of this polymer than there is N groups. So we don't really care what the N groups are, and in many cases they don't influence the properties of the polymer. But this long linear chain packs efficiently against itself, much in the same way you saw with the fatty acids. And so this tight packing results in stronger van der Waals interactions, and therefore a more rigid polymer. And that tends to be used, such linear polyethylene polymers are rigid enough that they have a separate classification, high density polyethylene. The recycling symbol with the 2 in the middle is usually how you indicate that. And you'll notice that the containers made from high density polyethylene are more robust, more difficult to bend than ones that are made from low density polyethylene. Where do we get low density polyethylene from? Well, depending on where you are in this process of polymerization, sorry, I'm going to just get rid of the end groups, and we'll use squiggly lines to indicate we're somewhere in the middle of the huge polymer. It turns out that a radical can actually abstract a hydrogen from one of the carbons in the polyethylene chain. And when that happens, you now have a new radical from which you can begin to add other ethylene monomers, and you can start elongating your chain from there. For example, here's the new bond, there would be a radical there, and then we'd add another ethylene unit, and so on. Until in the end, we might introduce a large number of branch points in this polymer, each with long chains on them. And what happens when you do this is the more branching you have, the less closely the polymer chains can pack. If they don't pack very closely, that means that their van der Waals interactions are weaker, and so so the branched polymer is softer and more pliable, and has a lower density, and this is called low density polyethylene, recycling number 4. And this is often used in plastic bags that are the bane of the environment. All right, so branching happens a lot during radical processes. It turns out that the linear polymer you have to get from a non-radical process, and that's called Ziegler-Natta catalysis, which we won't have time to talk about. But this is an example of how a change in structure results in a change in function. Low density polyethylene is branched, and the branching gives it its lower density and greater pliability. Linear polyethylene doesn't have branching, is more rigid, more firm, more robust, and higher density. So you'll see in general with polymers that structure changes in structure lead to changes in function. So in the short segment we'll switch to now, I'll show you an example of high-density polyethylene. Hey friends, I thought it'd be a good idea for us to go out in the yard and check on some things that involve polymers. So come on. This is our recycling bin. This milk jug is made from high-density polyethylene. You can tell that's the case because if you look at the bottom of the milk jug, you can see that symbol number 2 with HDPE on it. If instead of ethylene we use styrene, we get a polymer that looks like this, with phenyl groups on every other carbon. And of course, there would be branching as well in radical polymerization processes. Why are the phenyl groups on every other carbon? Well, imagine a radical attacking styrene. It's going to do so in a way that gives you an intermediate with the radical adjacent to the benzene ring, because that radical adjacent to the benzene ring is resonance stabilized. So the regioselectivity for radical polymerization of styrene is governed by resonance stabilization of the radical intermediate, and that's what happens again when we attack the next molecule of styrene and make the next radical. And as the polymerization progresses, we end up with this structure with phenyl groups on adjacent atoms. You've seen polystyrene polymers before when we talked about solid phase peptide synthesis on Merrifield resin. So the polymer here, this is the styrene starting material, and the polymer is called polystyrene. The abbreviation is PS, and this is number 6, recycling number 6. And now I'm going to show you a few video clips with examples of polystyrene polymers. They are used in containers, packing peanuts, sporks, other kinds of plastic containers. The polystyrene polymers also have an interesting property. They tend to be very dense, but you can change their structure by heating them up and mechanically pulling on them. That can generate very thin and very flexible sheets of plastic. And when you heat them up, they can snap back to a more dense state. And that's the basis of the wonderful technology known as shrinky dinks, which I will show you in the next video. This light and fit Greek yogurt is a staple around the Price family house, though you wouldn't know it from looking at me. But if you look at the bottom, you can see the number 6 symbol and the PS, which stands for polystyrene. Polystyrene has some interesting properties. Here I've got a thin stretched layer of polystyrene on which my son Dallin has drawn this picture of Baby Yoda, or more accurately, the child. You can stretch out the polystyrene and make it flexible, but when you heat it up, it snaps back down to its more compact and rigid state. So we're going to put this in the oven, heating it to about 325 degrees, and then we're going to see what the effects are on poor Baby Yoda. In the oven he goes, and now we'll watch through the All right, now he's done. We'll take him out of the oven. And there you go. Our little baby Yoda is much, much smaller than he used to be. And once he cools down, we'll pick him up and you'll see how he is no longer on a thin film of polystyrene. Another polymer comes from radical polymerization of propylene. Propylene is just the 3-carbon version of ethylene with a methyl group hanging off one of those carbons, and propylene has alternating methyl groups on alternating carbons. Again, the regioselectivity of the process is governed by radical stabilization. The same things that stabilize carbocations stabilize radicals. So being adjacent to methyl groups, which are weak electron donating groups, is stabilizing to that radical. So inductive electron donation by the methyl group. Polypropylene is labeled PP, and that's recycling number 5. And this is also used in a lot of containers. Polypropylene containers are resistant to mechanical stress and can also withstand a lot of organic solvents. So now here's a quick video clip of an example of polypropylene. And the Price family's been doing its part to go get takeout curbside delivery like the governor asked us to during this time of social distancing. This lid to container, if you look closely, is actually made of polypropylene. You can tell because of the 2 letters and because of the number 5. Another radical polymer that you have experience with is vinyl acetate. And when this polymer forms, I'm going to abbreviate the stuff here in green as OAC. You have acetate groups on adjacent atoms. And any of these radical processes are going to have branching. You've encountered polyvinyl acetate, or PVA, before in Elmer's glue, wood glue, paint, envelope adhesive. This polymer is thought to be fairly innocuous, fairly safe, which is why those of you that used to eat Elmer's glue are not dead. There's much more we could say about polymers, but I think we're coming to the end, folks. I do want to mention one thing about one last polymer which you've likely encountered in your life before. This molecule is vinyl acetate. Oh, shoot. Vinyl chloride. And it has the same sort of basic polyethylene structure with chlorine atoms on adjacent alternating carbons. Sorry. And again, the regioselectivity is governed by resonance stabilization of a radical adjacent to the chloro group, because the chloro group can be a weak electron donating group when adjacent to radicals and carbocations. You've heard of this polymer before, polyvinyl chloride, or PVC. And PVC tends to be hard and brittle, but it's useful in many different situations. In order to make it more flexible, people incorporate additives into the polymer. So one of the reasons that the polymer can be rigid is that it packs against itself really tightly. So if you can imagine these individual circles as individual units of the polymer, and they form an extended chain which can engage with itself in tight and stabilizing van der Waals interactions. And sometimes these interactions are so ordered that it's almost like the polymer forms a tight crystalline state, pseudo crystalline state. And because there's so much contact and van der Waals forces, this is a very rigid, inflexible state. One of the things you can do is to make the polymer more flexible is add a plasticizer. Now that's like saying, how do you make something more flexible? Well, you add something that makes it more flexible. A plasticizer is usually a small molecule that you add to the polymer, and the purpose of this small molecule is to replace some of the, to get into the crystalline state. We're going to abbreviate this molecule that is a plasticizer with just sure, let's color it red. And the purpose of this plasticizer is to intercalate into the interface between polymer chains as they're packing tightly against each other, and replace those extensive van der Waals interactions between polymer chains with van der Waals interactions between the polymer and the plasticizer. And that tends to loosen the polymer up, free it up from its crystalline state, and let it adopt a more amorphous state or flexible state. And of course, the reason it's more flexible is because it's now unwound and the polymer is not packing against itself quite as tightly. And PVC that's in the pseudocrystalline state might be PVC pipe like you use in sprinklers, sprinkler systems. PVC that's in the more amorphous state might be of the kind that you would find in a garden hose. So the next video clip will show you an example of that from my very own yard. The first polymer we're going to look at is polyvinyl chloride, or PVC. Here is my sprinkler box. I've spent many hours kneeling in the wood chips here trying to fix things inside this box. So, got the box cover there, and inside you've got valves that control when the water flows through. And then right here, oops, you can't see, right here is the PVC pipe. And the PVC pipe is quite rigid, and that can be a problem for sprinklers. If you leave water in the PVC pipe over the winter and the ground freezes, the water in the pipes will freeze too and expand, and the pipes are rigid enough that they won't expand with the water. Instead, they'll crack. And several years back, I didn't blow out my sprinklers, and when I went to turn them on in the spring, there was a great gushing pool of water coming out from under the lawn right there because a sprinkler pipe had cracked all the way down there. So that's a case where that's an example of how polymer properties can affect your everyday lives. All right, let's go ahead and put that down. Now I'm going to show you a different example of a polymer. Oh, there's some more PVC pipe in my backflow preventer. Had a bunch of trouble with that as well, though that's not polymer related. So we'll walk along. So here is another example of a polymer, the garden hose. It's also made of PVC, but as you can see, it's quite flexible. And the reason for that we'll explain in a little bit in the lecture, but it has to do with including what's called a plasticizer inside the hose. So here's another hose that I bought some years ago. It's also made of polyvinyl chloride, but as you can see, it's cracked. Right here, sort of where my thumb is. And the reason it's cracked is that over time, the plasticizer, that is the chemical that makes the plastic more bendy and more flexible, over time, that plasticizer, which is volatile, leaches out of the polymer, leaving the polymer to become more rigid. And then, of course, when you try to bend a rigid polymer, it starts to crack. So this hose is lots of fun when we start to turn on the water, and it'll spray back at you as well as out the nozzle. So as you saw there in that video, the plasticizer dibutyl, and I'm not ever sure how to pronounce this one, dibutyl phthalate, makes the garden hose flexible, but over time that volatile molecule leaches out of the polymer, leaving the polymer that's left behind much more rigid, and it can start to crack, which is what happened to my industrial strength garden hose that you guys just saw. Well, I think that's about it. There's so much more we could talk about, but we've run out of time. So I wish you the very best. Good luck on your final. It has been a pleasure to interact with you this semester. Please stay in touch, and as always, stay safe, stay healthy, and stay organic.